So now it's time for Professor Matthias Beller. You have already all your setup? Yeah? Okay. Matthias Beller studied chemistry at the University of Göttingen, Germany, and he completed his PhD thesis there. Then he spent 1 year in United States, and then he went to industry from 1991 to 1995. So this is quite uncommon, at least here in Spain. Then he moved to the Technical University of Munich as a professor for inorganic chemistry, and then he went back to Rostock to head the Institute for Organic Catalysis, which is currently named the Leibniz-Institut for Catalysis. Well, he has a terrible number, or very high number, not terrible number, of publications, over 900 publications, and with reviews, and over 120 patent applications. Professor Beller has many awards, and just I'm going to enlighten here the Carl Ziegler Prize from the German Chemical Society and the Carl Ziegler Foundation, which is one of the highest honors in the field of chemistry in Germany. His main activities, his current interest, are mostly focalized in iron-catalyzed oxidations and hydrogenation, hydroformylations, hydroaminomethylation and hydroamination, palladium and copper catalyzed cross-coupling reactions, rhodium and ruthenium catalyzed asymmetric hydrogenations. And the title is How Important Are Ligands in Catalysis? Teaching non-noble metals to behave like noble ones. The floor is yours. Thank you very much.
Thank you very much, Francesco, for this kind introduction. I would like to thank Clara and Eva Maria also for the organization and for inviting me. It's really a great pleasure coming to Barcelona, especially at this time of the year, coming from northern Germany, if you can. You just have to look at the weather in Rostock today, then you will realize it. But Barcelona is definitely always worthwhile to come. It's one of the most beautiful cities in Europe, probably in the world. So it's really a great pleasure being here. As you have heard, I'm a trained synthetic organic chemist. At least this is what I did in my PhD. And so at that time, I could not imagine to be invited to a conference focusing on phosphorus, boron, and silicon. But in the last years, phosphorus, of course, plays an important role in our chemistry for a long time, doing homogeneous catalysis. But in the last years, also boron and silicon became more important, but I will tell you a little bit about that at the end of my talk. Let me start very briefly with catalysis, because we have a section also on catalysis. We have various talks on catalysis, and I apologize if this is too simple. But of course, phosphorus specifically, it's not important as a material, but it's important because it's a component, a vital component of at least homogeneous catalysts. And why is catalysis so important? Because catalysis is so important because whenever we want to do chemical transformations, and that happens all the time in our body, in our environment, but also in industry, we try to convert, let's say, typically in industry, cheap, inexpensive starting materials, and to make more expensive, interesting products. But normally, the kinetic barrier for these transformations is pretty high, and that now catalysts come into the game. They allow you to develop different routes, actually, to do these conversions. And so the kinetic barrier is lower. Typically, then also the selectivity and the thermal stress on the transformation is lower. And in this way, you can control reactions. So catalysis, in some sense, is the science of controlling chemical reactivity. And although per se it's not good to have a catalyst in your solution because it's additional cost and you have to think about the recycling and all these things, it's a wonderful toolbox to control chemical reactivity. That's I think, the beauty of catalysis. And if you look at modern processes in industry, 90% of the processes in the classical chemical industry and the life science industry make use of catalysts. But most of the time, if we think about the development of catalysts and the use, actually, catalysis is pretty much still an empirical science. And I would like to show you that there are, of course, are concepts to develop improved catalysts. Nevertheless, I want to make also at this point already very clear, to a significant extent, catalysis is still an empirical science. And you have to, let's say, test a number of compounds. We have to make new ligands, like the ones Eva Maria showed, for example, unusual ones, because only then we will discover interesting new chemical reactivity. So because Maurizio is just sitting here in front of me, I did not know that, but I'd like to use this slide not only because it's, I think, very nice work from our group, but it's also, I think, a very typical example how people for a long time in organometallic catalysis thought about how ligands, or what is the role of a ligand in catalysis. And this, what you see here, is an ion complex coordinated by a tetradentate phosphine. And the first time this complex has been synthesized in the groups of Claudio Bianchini and Maurizio Peruzzini. And they have shown that this complex can be used for alkyne hydrogenation. And then for a long time, this complex was not used at all. And we became interested in that complex when we started some work in the area, let's say, of energy storage materials. I will show you one more slide from that area. But I don't want to talk much more about this area. This is also 1/3 of my group is doing energy-related research now. But at that time, it was still at the beginning when we started this work, we were interested in this reaction, hydrogenation of carbon dioxide to formic acid, dehydrogenation of formic acid to carbon dioxide and hydrogen. And this is in general, it's one of the principal reactions to store hydrogen, or to think about hydrogen storage materials. Of course, the hydrogen density of formic acid for a hydrogen storage material is not perfect. Methanol, methane, they have a much better density, energy density. But this is one of the very few reactions where you more or less under thermoneutral conditions can attach a hydrogen molecule to an acceptor and also can dehydrogenate the molecule. And this is intrinsically an advantage if you think about energy storage. So this ion complex, after 1.5 years of testing all kinds of ion complexes, was the only one who was really efficient for that. In fact, it was so efficient that it comes close to the noble metal catalysts, which are known for this type of reaction. But why did I show you this complex? Because I showed you this complex because I think it's very typical for our thinking in organometallic chemistry for a long time. Because if you look at the chemistry, will go into detail, you have to ask me afterwards. But if you look at the chemistry behind that reaction, what you will see is that the ligand does not play a direct role in this catalysis. It's there for stirring the electronic and the sterics of the metal center. Each of the catalytic steps, deactivation or so, activation, they take place on this metal center. And this is, I think, our traditional belief of organometallic chemistry. If you think about the very important reaction, Wilkinson's complex, hydrogenation, we have heard hydroformylation just before. If you look at these reactions, there is a metal center, and every single catalytic step, everything takes place on the metal. And we think the phosphor ligands are ubiquitous in this type of chemistry. They are only there to direct or govern the sterics and the electronics. But I believe this is wrong. In recent years, not only in homogeneous catalysis, but more and more in homogeneous catalysis, people have shown that the ligand actively participates in the catalysis. And this is not only true in homogeneous catalysis, in fact, it's true all the time in heterogeneous catalysis and biocatalysis. If you think about some modification of an enzyme at a remote function of the active center, this remote functionalization has tremendous impact on catalysis, although it's not directly governs the active center. The same is true in heterogeneous catalysis. Typically, there is hundreds, probably thousands of different catalytic active centers on a surface. And if we think about silica-based materials or boron oxide or something, there is much more than one, let's say, active metal center if you dope this on a surface. And of course, the surface plays an important role in the catalysis. So this traditional belief, we have a metal center, everything is governed by the metal center in catalysis, this is, I believe, wrong. And so you can easily visualize or think about that if you like to do a catalytic reaction, or if you like to move that stick. If you have one function, or if you have one center which should do all the jobs, that's my simple view on that, it's very difficult. If you have multiple centers coming together, which one of the centers probably lowers the kinetic barrier for a certain step, another one for another step also, and the overall result is that catalysis proceeds in a better way, or the transformation. And some of the ligands which are now used in homogeneous catalysis are so-called non-innocent ligands. Non-innocent ligands, it's a fashionable term which is used for ligands which actively participate in catalysis. And one of the examples is this, are these P and P pincer type complexes, or ligands which are, again, of course, we are standing here on the shoulders of very capable scientists. Giraffe and Coten, for example, since 2000, David Milstein, they made this chemistry very popular. But if you look at the catalytic steps of this, and again, it's an energy-related reaction, it's the dehydrogenation of methanol, or the hydrogenation of carbonate or carbon dioxide to methanol. And you can go basically in this direction or this direction, depending on the conditions. But now if you look at the catalytic steps of these reactions, then you will see the ligand is participating in this type of catalysis. It's not only everything takes place on the metal. We got inspired, or we came to this chemistry when we saw that chemists from Takasago published this, now it's called macho complex, this macho complex for hydrogenation of esters, and we were interested in this hydrogenation, dehydrogenation, hydrogenation of carbon dioxide, dehydrogenation of the hydrogenation products of carbon dioxide. And you can easily dehydrogenate, for example, isopropanol, benzyl alcohol, things like that. There is hundreds of ruthenium catalysts, but this was the first homogeneous catalyst which was capable to dehydrogenate methanol. And methanol is much more difficult to dehydrogenate than other alcohols. And again, this is in the interest of methanol reforming and energy storage. Interesting. So this type of complexes, just briefly, you cannot use them only for dehydrogenation methanol or other alcohols. You can use them for the dehydrogenation of all kinds of polyols. And the simple polyol would be, for example, carbohydrates, glucose, but even, and this was work, for example, of Peter Sponholz. He used cellulose acetate. Cellulose acetate, this is the material for cigarette filters. And so he dehydrogenated, for example, used cigarette filters. The ugly part of the work was to collect the cigarette filters and then to cut them down, and then you can dehydrogenate them with these type of complexes. So any type of, let's say, alcohol bond can be, in principle, dehydrogenated with that. And in my talk, in the title of my talk, I mentioned how to teach non-noble metals to behave like noble ones. This is, of course, a bit provocative, but in fact, I believe, because of that thinking, it's not the metal alone which is important in catalysis. We can tune metal centers to behave, let's say, also non-noble metal centers to behave like noble ones. And if, of course, if your catalytic active system is more than the metal alone, it's much more easy to change, let's say, the catalytic behavior of the metal center. And since more than 15 years, we are especially interested with respect to homogeneous catalysis to make organometallic iron-based complexes and to use them in catalysis, and we have used them for various types of redox chemistry since then. And we are interested in this type of chemistry not because, like you read in all the publication, iron is cheap, iron is easily available. No, it's mainly because we thought iron offers innovation potential or opportunities, because much less was known at that time when we started in this type of chemistry. And so it was more or less logic that Elisabetta Alberico from the CNR in Italy, in Sassari, when she came to Rostock as a visiting scientist, and she typically comes 1 to 2 months per year. Fortunately, we are very grateful to her. When she came, and she's a fantastic organometallic chemist, that she tried to make the iron-based complex of the ruthenium macho when we had the first reactivity. And Elisabetta was the first who synthesized also this complex, and we were really surprised if you compare the characteristics of the complex. The iron complex didn't differ much from the ruthenium-based one. And when we used the iron-based complex under the same conditions like the ruthenium one, we were really surprised that the behavior is more or less similar. Of course, with the ruthenium we had under optimized conditions, we could get, for example, for methanol dehydrogenation, turnover numbers of more than 400,000. But with the iron one, we also get 200,000 under optimized conditions. So it's a very efficient catalytic system. The rate determining step, if you look at into the mechanism of this reaction, it's the dehydrogenation of the formic acid. It's not the dehydrogenation of the methanol, for example, or the gamdiol or formaldehyde. So the chemistry, again, in the catalytic cycle, it's pretty much the same. And so this was really surprising, because normally when you have a ruthenium complex and you try to make the same iron-based complex, first of all, it's often difficult to get the same complex, and second, even if you get it, the catalysis normally is not the same. But here, it's more or less the same. So there is something special. And the special is, of course, that the ligand is participating in the catalysis in this type of chemistry. And you can understand this more carefully when you look at the elementary steps of the reactivity of that complex. And one of the, I think, very nice experiments we did over the years in Rostock is the reaction of this basically isolated iron amido complex, because you can also generate this complex, and if you add hydrogen at 1 bar at room temperature in an NMR tube to this complex, you can observe the equilibrium between this reaction. And you should imagine now, this is a reaction, this is the basic reaction for all types of hydrogenation and hydroformylation chemistry. You have activation of hydrogen by a defined metal center. But the metal center is not ruthenium, iridium, rhodium, which is very common for all this chemistry. It's an iron-based system. And the iron center allows for the activation of hydrogen at 1 bar and room temperature. The only defined system which could do this before were the iron-based hydrogenases. They also can do activation of hydrogen at low temperature and low pressure. And Haijun Zhao, a theoretician in our institute, he calculated this reaction parallel to our experimental, let's say, or mechanistic work, and he showed very nicely that, again, this hydrogenation, dehydrogenation is not strongly exothermic in one direction. So it's really, it's a more or less thermoneutral reaction. And if you add hydrogen pressure to the system, of course, you shift the equilibrium to this, and you can use this compound then, for example, for hydrogenation reaction. So it's a hydrogenation catalyst. If you work in an open flask, so not under pressure, you can use this chemistry for dehydrogenation catalysis. And I will give you some examples what we can do with these type of. So in principle, you can use this, but not only the iron one, of course, the ruthenium, and as you will see, other metal-based systems too for this chemistry to do hydrogenation, dehydrogenation chemistry. You can not only add hydrogen to carbonyl compounds. As you will see in a minute, you can dehydrogenate alcohols to carbonyl compounds. You can hydrogenate especially polarized, but not only polarized, double and triple bonds, carbon-carbon ones, but also nitrogen imines. And you can also do the dehydrogenation-based chemistry. So they are very valuable catalysts for all kinds of redox chemistry. Here you see one example. It's hydrogenation of nitriles. And you will also see that the chemistry differs from the typical chemistry where you use noble metal catalysts for this type of chemistry. So we have this as a pre-catalyst. So the hydride alone is also stable, but if you add borane, if you add BH3 to this one, you get the borate complex, which is more stable. at 40 degrees, you can liberate this complex, and then basically you can transfer the proton from the amine and the hydride from the iron to polarized double bonds. So it's not, because we have two hydrides here on the metal center, it's not a dihydride mechanism from the metal center, but we are adding a hydride and a proton from the catalyst system. In this way, the ligand participates in the catalysis. So then you get the imine is hydrogenated again, and the amido complex at low temperature also activates hydrogen to regenerate the catalyst. And Pierre Disneuf, whom I know for a long time, who did fantastic, he and his group did fantastic work, especially on ruthenium catalyst. I always like to tell the story after we had a discussion, and he said to me, because we were interested and tried to convince him that iron is interesting, he said, be honest, in most cases, ruthenium is the better iron. And what he meant by this is we publish all the time iron-catalyzed reaction, but in reality, ruthenium is better than iron in these reactions. And if we can, even if we use 5 mol% of an iron complex, and of course we have to think about the price of the ligand, here is the price the determining factor, not the metal. And we can do the catalysis, let's say, with ruthenium, with 10,000 of turnover numbers. Ruthenium is much better than iron, of course. It's scientifically interesting, but it's not of practical value. But of course, we're doing this type of chemistry to discover cases where iron is the better ruthenium. So that, and this is one of the reactions. That was because if you look at the hydrogenation of aliphatic nitriles, published several ruthenium catalysts for aromatic nitrile hydrogen, but if you look at aliphatic, especially adipodinitrile, ruthenium is not so good. And we compared the iron and the ruthenium catalysts exactly for this reaction. And here, to our delight, iron was by a factor 2 to 5 better than the ruthenium system. So it's really also, it's not only interesting to develop this chemistry because, let's say, it's another metal, but it can be better also than previous state-of-the-art catalyst systems. So you can do much more with this type of chemistry, just a few things. You can do dehydrogenation reaction. I showed you the hydrogenation. This is dehydrogenation reaction. If you have polyols, then you dehydrogenate. And if you have a functional group in the molecule, you can easily, let's say, do addition, and then you make lactones. You can make esters by dehydrogenation. And the interesting thing is you're doing oxidations. That's an unusual way of doing oxidations. Most of the time when we're doing oxidation, we have to use oxidants. And oxidants kill our ligands typically in catalysis because the ligands are also vulnerable to oxidation reaction. This is an oxidation reaction under reductive conditions because we generate hydrogen as a side product. So that's an interesting concept, by the way, for oxidation chemistry. And you can not only use iron, iridium, ruthenium, which has been very well studied in this type of chemistry. This is a very recent example. We are writing up the results of cobalt for this type of chemistry. So the corresponding cobalt pincer complexes. This is a reaction which I've shown you for the iron, the dehydrogenation of formic acid. This is a cobalt-based system, which works very well. So you can do a lot, let's say, you can play with the metal. And when we saw that we can play with the metal, we asked ourselves, so I showed you one example of cobalt, I showed you ruthenium, iron there, and the mechanism of these different metal complexes is similar. In all the cases, the ligand participates. So when we get these results, we thought ourselves, can we even play this game a little bit further? In a sense, let's say, do hydrogenation reactions with a metal which is not known for hydrogenation reactions. If we put around the environment, let's say, which allows iron, cobalt, and all the other metals to be to generate hydrogenation catalysts, can we do this with a metal which is not known to do hydrogenations? Because you can say, I've shown you this with cobalt, rhodium, there's other groups, iridium also, but you might say there is lots of other complexes which can do this with these metals. But we thought, can we use a metal for this which is not known for hydrogenation? If you think about metal for hydrogenation chemistry which is not known, then one of the few systems which is not known, at least to my knowledge, before our work is manganese. Manganese, again, it's a non-toxic metal. It's very available also, so this makes it interesting again, price-wise, but again, I should say the ligand is determining here. And it was Saravana Elangovan, a joint postdoc with the group of Christophe Darcel in Rennes, who came to our lab, and he synthesized this manganese-1 complex. Manganese-1 is somewhat unusual, but you can buy manganese pentacarbonyl bromide, and if you add this tridentate ligand to that, you immediately get this nice air and water stable complex. This air and water stable complex you can put here on the shelf, come on Thursday again, and it's still stable. So it's really a nice, very stable complex. If you generate the active species, either by beta hydride elimination or by hydrogenation, of course, the complex becomes sensitive, and you have to use it under Schlenk techniques. We observed the hydride, and now if you look at that complex compared to the iron before, you see it's not a dihydride because it's manganese-1, but you see it has the same, let's say, microstructure or same principal structure like before. And indeed, when we use this, it works like a dehydrogenation and hydrogenation catalyst. So you can do dehydrogenation. Methanol dehydrogenation, I started with that with ruthenium, 400,000 turnover numbers, iron, 200,000. Manganese is pretty lousy for that, but not so bad still. It still allows for a turnover number of 20,000 methanol molecules. So 20,000 methanol molecules are dehydrogenated on average per manganese system. And of course, you can do the reverse. You can do hydrogenation chemistry, for example, ketones to amines. You can do hydrogen autotransfer chemistry, like Miguel Jus called or coined this term. Jonathan Williams calls it hydrogen borrowing chemistry, and this chemistry you can use. And also, Miguel has shown beautiful examples with Knövenagel combination. You can use this for making carbon-carbon bonds from alcohols, or you can make amines by adding amines in this. And this is a very nice way to convert alcohols into carbon-carbon or carbon-nitrogen bonds without any activation. And all the catalysts I've shown you, if they are hydrogenation and dehydrogenation catalysts, allow for this type of chemistry, because in the first step you need a dehydrogenation catalyst, and in the third step, then you need a hydrogenation catalyst. And this is exactly what these things are doing. And because they work very well with methanol, which is an alcohol which is difficult to dehydrogenate, they are especially work very well, let's say, to do, for example, methylation type reactions. You can make N-methylation, which is a privileged structure, for example, in pharmaceuticals. In this way, the chemistry is quite interesting. Here, I show you some examples of hydrogenation reactions. This is a manganese-based hydrogenation with these Pincer complexes, and you can dehydrogenate alcohols, aldehydes, also polarized double bonds. Here an example with this type of complex. So in principle, you can teach manganese to become a hydrogenation catalyst if you put the right environment or structure around it. And this is the key point is the ligand participates in the catalysis. So it's multifunctional catalysis. You can even do asymmetric hydrogenations. I will not, in the interest of time, go into details here. Crucial for this manganese-based reaction, as well as for the iron and the ruthenium ones, is that because of this metal amide unit which you have, which is in close proximity because of the phosphorus donor atoms, because these metal amido system, this allows for an activation, a heterolytic activation of hydrogen, so it's different like on a noble metal surface. You have the hydrogen molecule coming, let's say, to the catalytic active center. It gets polarized, and the proton goes to the amido system, and the hydride goes to the metal center. And it's not important if it's there ruthenium, iridium, manganese, or iron. So all kinds of metal atoms which can stabilize the hydride there can be used in this type of chemistry. So at the very end, I would like to show you that this type of chemistry can be also used in applications. And we have a ligand system which follows this principle, which is now used in pilot plant scale with Evonik, and we hope, of course, it will become a process, but this is still too early to say. And in our institute, we are especially devoted towards this transfer from basic research to practical applications. And now I'm switching a little bit to the applied point of view. And I just want to mention here, if you really want, I want to make clear also, of course, not everything which has to do with catalysis has to be applied, very clear. It's very important that we do basic research, that we make new compounds, because only then we can discover new chemistry. But if you want to work on an applied case, you have to, let's say, fulfill certain industrial requirements with respect to the price of the catalyst and so on. And the example I would like to show you is carbonylation-based chemistry. And this carbonylation-based chemistry, carbonylations are run on a 10 million ton scale, or more than 10 million ton scale in industry. Often it's that homogeneous catalysis is not done on large scale, but carbonylation is a nice example that it's done, so hydroformylation and other carbonylation reactions. And the metals which are used in this chemistry are rhodium, specifically in hydroformylation, iridium, if you think about, for example, the Cativa process, methanol carbonylation, or palladium, if you think alkoxycarbonylation reaction. And this is the example I want to show you. This is one of the industrial processes. 2 plants exist. A third one is built. It's very beautiful chemistry developed by Graham Eastham in the UK, Lucite. And this is one of the processes for methyl methacrylate. And the palladium-catalyzed carbonylation step is here from this very simple molecule, ethylene, to methylpropionate. This is the commercially available catalyst, or the ligand for the commercially available catalyst. If you look, you might say, okay, this looks like an expensive phosphine, but this phosphine is used in at least 2 multi-100,000 ton scale plants. So you can imagine the catalysis should be very efficient if you think about the price also of methyl methacrylate, which is not a very, let's say, high price molecule also. So it's extremely efficient catalysis. We came into this chemistry by cooperation with an industrial colleague, Robert Franke at Evonik, and they were interested. They asked us, could you do carbonylations not, let's say, with the simple terminal or internal olefins, which is very common nowadays. But we have a feedstock. This feedstock is called dibutene, and we have a feedstock, and in this feedstock we have notoriously unreactive olefins, because this feedstock, dibutene sounds like a nice, clear feedstock, but in reality, dibutene is a mixture of more than 30 isomers. It's a mixture of the dimerization products of butene, and if you dimerize butene, you make octenes, methylheptenes, dimethylhexenes, and all kinds of olefin isomers. And in these olefin isomers, you have notoriously unreactive tri- and tetra-substituted ones. And there is no commercial catalyst which can do these type of reactions. If you now look at the catalytic cycle of these type of reactions, palladium is the key point. We thought to address this problem, if we can, let's say, add function into the ligand which allow actually to speed up the rate-limiting step of this reaction. And it's a long story. I cannot, because I got to sign, I'm more or less finished. I have to finish here. No, but if you're interested, I can tell you afterwards also in more detail. So we looked carefully what is the rate-limiting step in this reaction. And we were really surprised to find that it's the addition of the nucleophile. You need a very active catalyst system like the Lucite ligand, but if you use the Lucite ligand in this chemistry, the rate-limiting step is the attack of the nucleophile on the palladium acyl complex. And this is understandable when you know that palladium hydrides are very acidic compounds. So it's an acidic medium. And under acidic medium, the attack of a nucleophile on acyl can be rate-limiting. So we thought, can we add function to our catalyst system, which can circumvent or lowers this activation barrier? And we did this, of course, when you would like to speed up, let's say, an attack of a nucleophile on an acyl species, you think immediately about base. But if you add base to such systems, they don't work at all because they take away the palladium hydride. So the catalysis doesn't work. So what we did is we added base into the ligand. So again, it becomes multifunctional, now not by dehydrogenation, but we put in a basic ligand. And this is the thing Helfried Neumann did. And you see here some reactions, some model reaction. they all do not work, only basically this new ligand. And this is the activity difference of the systems. So simply adding additional function into your system tremendously speeds up the system. And this is the pilot plant process, which is now used dibutene at Evonik. And if you can do this, then you can also do all kinds of other reactions, remote functionalization reactions, and so on. So this is actually what I wanted to tell you. I don't want to go into other new reactions with these type of ligands, which allow, so making a new ligand allow you then also for new catalytic transformations. I have to thank all the people who were behind this picture. So, and who were behind this work. You have seen the names, sometimes the pictures of them, and I'm specifically thankful again for the organizers, and I'm happy to answer questions. Thank you.
Very interesting talk, which goes in parallel with the nice title you had. Okay, it's time for questions.
Yeah.
Sorry.
Very nice talk, Matthias.
Thank you.
Thank you. In nature, iron-based catalysts are usually always using high-spin, low-spin switches to be more active at a certain stage of the catalytic cycle. And there, of course, is an advantage or difference from 4D and 5D metals. Does this play a role in your iron-based catalysts?
I don't feel that in this iron-based pincer, it doesn't play a role. But we have other systems, I think, where this is a crucial point. But in this type of iron-based systems, it normally doesn't play a role.
Yeah, carbonyl, phosphine. Yeah.
Yeah, this is an important point. Just briefly, I didn't elaborate on that. For most of the systems, cobalt is different. You need carbonyl ligands to stabilize the complexes. This is true. So we're still trying to make, and we have now some. We tried for a long time also. But to replace this carbonyl ligand in order to make the catalysts more more changeable, so that you have more versatile system. But it was very difficult. But we can talk afterwards about that.
Some other questions? I have one. You mentioned at the beginning that you convert sucrose, some kind of sugars, and at the end you produce carbon dioxide and hydrogen.
Yes.
I am wondering if that could be extended to cellulose.
Yes, in fact we did. So we used cellulose, and this is also this was work, sorry, this was work by a very talented Chinese postdoctoral student, Yang Li. She is now professor in Xi'an, and she continues that work. There it is. Sorry. So this is Yang. We started that work in Rostock when we used, for example, cellulose acetate, and you see here we use fructose, glucose, cellobiose, but we also used cellulose acetate, the cigarette filters, and other things. And in this very recent work here, I think I should say it's mainly the work of the group Yang Li. We supported that. She developed really a highly efficient system which works because it's steam reforming type chemistry, or steam reforming of carbohydrates, for example. But you can do this at temperatures of around 100, 120, 130 degrees. So it's relatively low temperature. And the yields of hydrogen for this type of chemistry are above 80% overall. So it's really a very high. Initially we had lower yield, but now it's very high.
So it's necessary first to solubilize the cellulose. To pass it to acetate and then operate.
No, you can also use directly cellulose. You can even use lignocellulose. The way we are doing it now is the following. We are doing initially a part oxidation chemistry using phosphomolybdates, oxygen, And then after, the main point of the cellulose or lignocellulose, for example, is converted to formic acid. And then the catalyst does the dehydrogenation of this mixture of alcohols and formic acid.
Okay. Very interesting. So, another question? So if not, we can join me to thank Matthias and Eva for the interesting talks of this morning.